that is going on nearby. And here you see an example of why is that so.
Yeah.
That's fine, I'll try with that. This is the center of a giant molecular cloud core. It is nearby 2 kiloparsecs seamless picture in the mid-infrared, so you see very small dust particles. And the structure overall is very complex. And that is true in general for star formation. If you have the resolution, it's usually 3D. So there's no way around that. Even if you have an accretion disk in some approximation, you can see, but if you resolve that accretion disk, usually it is a 3D thing because it is warped, it has spirals or so. Furthermore, we have a real problem here because the optical depth, as wavelengths we're interested in, often varies, and it alternates even between 0 and something very big. So numerically that is a problem, or has been a problem. But it means also that all the objects we are interested in, especially how they form, is deeply obscured at the wavelengths where we have the best resolution. And unfortunately, these objects are close enough that we cannot make an easy model. Like in cosmology, where you fit 4 data points, we have to fit with one model different images, 4,000 pixels or so. That's the order of model agreement we have to achieve. And moreover, it is very interesting to note that although stars are the most prominent ingredients of astronomy, we still do not know, despite all the telescopes we have and the modeling, how to form them. And also the planet we are standing on is quite unclear how to form it. We have some ideas, but still it is quite unclear. To give you an impression, especially those who do not do star formation daily, these are the processes that are currently discussed to play a role for the solar type low-mass stars. They form in molecular cloud cores by gravitational collapse, but the ingredients are quite unclear. What effect do magnetic fields have? How is the fragmentation going on? At what time? Turbulence is playing a role, we know that, but there might be also external initialization of that process. We have dust in there in quite an amount. It will cool, but also the line cooling is important because it is very cold as matter. You have all sorts of molecules, a rich chemistry. And the radiation is transporting energy, so you better do that right. And also it is the main carrier of all the information we get from the system. To start with, I would like to show you the equation. It will be just one slide, don't worry. Radiation transport is a nice thing.
People see them.
That's right, yeah. It's an intro. It is a very simple equation compared to MHD, but it is very hard to solve because MHD is a 4D problem, and radiative transfer, as most of you know very well, is a 7D problem. So you can forget about having a very nice resolution as in MHD simulations that run nowadays. So let's start with the...
Well done. We have
here. So the very simplest one is a steady state one where you just calculate the change of the intensity. It's a 6D quantity here you have to solve for, and you give a certain direction and then you evaluate the change in that direction, and as you know it's just an exponential solution, and all the physics go into the extinction here, scattering, absorption. The solution vector due to the high dimensionality is quite large though, but that can be solved easily. Once you allow for the dust to re-emit, you get the Planck function, so the emissivity contains the temperature. The temperature might be determined by, let's say, the accretion process, and it's quite fine. You just take it from your simulation. But there might be parts of your domain where the radiation, the temperature is determined by the radiation field itself, and you do the well-known iteration to the local energy density equilibrium equation. But this is very unfortunate because you couple the differential equation here to a double integral equation. So you see, we sum over all the directions and the wavelengths to get what we observe, and then you re-emit it, and again there's an integral. So if you combine the equations, put them in a large linear system, and you want to solve them with new modern metric solvers, we did this for 1 year in collaboration with mathematicians. It's not working. The problem is that here these integrals mean that you have parts of the matrix which have non-zero elements in blocks. So you can kind of use normal conic gradient methods which apply nicely to sparse systems. But the very bad news is most of the information we get is the high resolution range, and that's short frequencies, optical. And there, scattering with dust particles is very important, and you see, you get it in the source function, so it's a plus, and you get a phase function here determining how the scattering goes from one direction to the other. And this is an integral term, so you get an integral differential equation. That means a straight normal equation of second kind, as a mathematician would say, very hard to solve. And that's a real problem, yes? Yes. Solve the full thing. You would be able to solve it more easily if the phase function would be 1. So for dust particles, people claim, why not using the isotropic approach, saying, well, the isotropic scattering, so it's working. But here you see the phase function of a typical interstellar medium dust particle silicate, just normal mesosphere, very simple model, and you see radiation that comes in is scattered here at the origin, is then emitted, and you see the intensity, it is forward scattering. So it is anisotropic scattering, and the integral cannot be easily neglected or approximated. And that is the real problem when we want to model images with nice resolution. So forget about the isotropic scattering. The solution methods, some have been mentioned yesterday, roughly ray tracing, Monte Carlo, you solve it by finite difference in so moments if your radiation field is not so anisotropic. Spectral methods, finite volume methods are now used, and with that chairman I better also mention simplex tessellation on a very complex grid. Let's go through the 3-1 I showed in the beginning. Monte Carlo is not a solution technique. It is a simulation technique. That means you simulate the physical process and hope to get close to the solution of the transfer equation at the end. It has huge advantages. You calculate each interaction precisely. That means, for example, you can produce a polarization map. It's very flexible. It doesn't matter if your complex structure is bothering you, and the code development is within one PhD lifetime, and that's the reason actually why so many Monte Carlo codes pop up lately. It has a main disadvantage, and that is there is no explicit error control. And that's not so bad if you have a 1D problem. 2D problem is still okay, but if you have a complex structure, you don't know what you're doing. That's what I'm saying here. It's very hard to control the area. You might be right, but you don't know. And there were problems with high and low optical depth. They have been solved meanwhile, in my view. Then ray tracing, it's the other way. You just integrate along the line. And it is very accurate. You can use high order Runge-Kutta, and that means you can do the error control implicitly, but it is expensive. But you can do adaptive set size control, so you do large sets where you can do it, and that again saves you some time, but nevertheless you often call the density function with that technique, and that's very expensive. Let's say if you calculate it for an AMR grid or any other grid you have by interpolation. There have been problems with high optical depths which have been solved. Or you discretize, let's say, finite differencing or so directly on a good grid. Again, you can handle the errors and calculate them explicitly. It is also flexible depending on your grid. Numerical diffusion is a real problem with this solution, and we tried this one in many papers. It is very hard because the beam is smearing, so I wouldn't recommend this for complex configurations. And also, there's usually a cost direction resolution which can kill you when you apply it to model something. So what we currently do is, depending on the problem, we create a grid knowing the density structure, then we propagate the source energy, let's say the star to the interstellar radiation field. For each cell we store absorbed energy and the scattering intensity for each wavelength. Then we do propagate the scattered radiation. The hope is that we do not have to do all these rays from all the cells, because the intensity drops quickly. There's a strong absorption, that means the photon is strong, you don't have to follow that ray. Or the energy is distributed due to the scattering process, and also, in general, the efficiency of scattering is not 1. So hopefully most of these rays cancel out. Then you have the scattered radiation field, but still you want maybe to know the temperature, maybe even self-consistent, and then you go to 3 micron, because the emission is due to the sublimation temperature of the dust. It's not at shorter wavelengths, and their scattering is not really important. So for many applications, you can neglect scattering. That decouples the problem a bit. And also you can go to coarser grid because in mid-infrared the absorption is much less, and also scattering, like I said. So you don't have so many cells, but then you do cell illumination. That's painful, but it is good because with every cell you miss, you might miss important physics. If in this cell everything is going on, and you might have a problem with the refining in this grid because of the number of cells or so, then still you get all contributions, while if you have a fixed direction grid, you might miss it. Also, ray tracing with high optical depths, we have solved that problem, we believe, by now putting the diffusion limit into the ray tracer. That means you can quickly cross the optical thick case, and the acceleration and the star formation applications we had in mind in that paper were about 1,000, so that's quite efficient. And as I mentioned, there is an SED benchmark, not a radiative transfer benchmark. That would include images as well. We did one 3D image comparison with the Monte Carlo code. There were substantial differences. So there's a lot of work to do. And even in this project, we had to fight a long way to really get to consistent results. So we can have a look here at this configuration with the star and the disk. But the more important point for you, and that is why I changed my talk substantially yesterday night, is what can radiative transfer do for you guys doing MHD simulations. First, and obviously, you provide the 3D density and if you want the temperature, and then we calculate the images. That's a standard application, and it means we calculate the images given the telescope. So we can produce an ALMA image, for example, from your calculation can tell you, if you want to see that feature, better look in the atmospheric window at that and that frequency. And then, what has not been done so far extensively is tests of your radiative transfer modules in your calculation. And I will show one example where this work is in progress called AMR massive disk calculation. And I will show two examples for radiative transfer in the inverse way. And that is, so to say, the holy grail of radiative transfer. You have images at different wavelengths, and from that you decompose the density structure and the temperature structure in an inverse way. And then we provide you, let's say, with the density structure, you plug it into your code, assume maybe a velocity field, and then you can work with it. And I will show you two examples of that. So that's possible nowadays. Interesting enough. This is coupled to astrophysical highlights, and I will concentrate on low mass star formation and high mass star formation. And here I show, for example, the largest circumstellar disk structure that is known so far. I concentrate here a bit about the disk because we will later hear more disk talk, so maybe it's interesting for these people. The standard procedure is take an SPH simulation data cube in this case, and we produce at the different wavelengths and the different time steps of this core collapse evolution, we produce the corresponding images. These are not visualizations, that's very important to say. Of course, you have your tools to visualize your density in cuts or so. These are the real images. And if you would have the resolution with the telescopes, you indeed could directly say which feature of your calculation can be seen. There's another example here. It's the first simulation of its kind because it is a 3D HD collapse simulation of a massive core that has not been done so far by using the Orion code, MHD AMR code, that has the flux-limited diffusion inside. And this is new, run by Richard Klein, Mark Frumholz, and Chris McKee. And I can't show you the details. It's a very nice thing showing cryostructures and massive objects forming inside. I got that huge data set, and they said, do your radiative transfer on it. And even when I scanned through the grid by ray tracing simply, I saw that my current algorithm is too slow, because the number of AMR cells for such applications is so high that the speed is everything here. I mean, these calculations are massive parallel and they run for months, so it's quite a lot of effort going into these. So I did it for the millimeter where it's most easy, and you see one advantage of applying now the radiative transfer is I got this when I looked on top of the full volume. This is the inner part, so this little dot. But you saw there are slight discontinuities I detected in the millimeter, and there are discontinuities you wouldn't see when you look at the density distribution. But if you add them up by column density, as you do in millimeter, you see them. So that's a nice advantage. If you collaborate with radiative transfer guys, they can show you little errors. Meanwhile, they have fixed that obvious problem in the code. its advantage.
So this radiator transfer does not have any back reaction on the flow?
In this case, there would be no way. I mean, already we are at the computer limit with the simulation of the MHD. And as you know, if you run with the same accuracy a 70 and a 40 column, 99% of all the computation time would go to the radiator transfer and 1% to the MHD. So there's no way to simultaneously run both. But of course they have, like I said, the diffusion limit, the flux limited diffusion approximation in there. So there's radiator transfer in there, but it is crude, as we know. And one part of the project will be to test. That's what I will do. They have temperatures, I will calculate temperatures. I know all the sources, so I can compare and say, in this part of the domain, your radiator transfer is crude. And
Even
that's
to do one time slice,
Yeah.
comparison, is
Yeah.
demanding right now?
No, I will produce images here and I will calculate it here, but it is hard. That's quite clear. But for one time set I can do, but not for sequence. Let me quickly go to the inverse radiator transfer. So what you need is, you take for example rho 50 is a nearby low mass star forming cloud, 140 parsecs away only, and you take such a core that is seen in absorption in the mid-infrared and in emission in the millimeter. So you need more than one wavelength that this method is working. Then you, with basis function, you choose carefully, like here Gaussians, you choose a setup that you model the column density. You wind up with 150 parameters in this case. We do 3D modeling. There's no way that you can get around this to have many parameters, but you fix simultaneously 10 times more pixels. So this problem is well constrained, and we tested this quite efficiently. And the optimization tool is simulated annealing, but you could also use genetic algorithms or other tools. Here you see the observed map at 15 and 7 micron. Here you see the model maps. So the fit is quite okay. The question is how you reveal now the 3D information that is hidden due to the projection on the sky. And the idea is that in the millimeter, the emissivity depends on the temperature. If you have a radiation field from outside and you have a compact configuration, let's say a sphere, then it's cold inside. If you stretch by converting the mass, then the radiation can penetrate deeper and the temperature will change. So it is sensitive to the elongation in the 3D line, and that means we can decompose and find this. Still, you see some remnants from the basis function, and nowadays we use more basis function and different ones, but nevertheless, you see overall, you see iso density surfaces, I should say, at two levels, one semi-transparent, and you see it's a very complex structure, and it's not at all two clumps as people thought. We have applied this to the most famous core. It is in this region lots of stars, isolated, and throughout this, in this nature paper, took this one because it looked nice and compact. All the others are quite fluffy and filigree. And so he zoomed in with the 8-meter telescope, BLT, looked at it, and you see that the stars, of course, are obscured by the cloud. But if you look in near infrared, you can see the stars. And by this you can make a very nice column density profile, and this was a fit from the nature paper. And he did it with a very simple model, and that is an isothermal sphere that is balanced by thermal pressure and gravitation. So the claim was, all the cores are like this. They're just a balance, and that's interesting for the HD guys, really, that there is this simple, very simple, nearly isothermal gas sphere explaining it so well. So we did it in 3D. I want to spare you with the details. We got maps at different wavelengths, and here's the outcome. Again, an isodensity surface, and you see it's not a sphere, that's quite obvious. But we found out that by calculating in each point the gravitational force, as we have the 3D density structure and the temperature, as well as the isothermal pressure gradient, that indeed it is close to this balance that was claimed. But not based on a single density profile. Here it is really 3D modeling, and this is quite interesting to know. This one is also wobbling quite a bit, as we know from radial measurements, so we call it the Bona-Ebert jelly.
If you impose the condition of equilibrium on your solution.
No, that's a nice thing.
I'm asking you, if you did,
If I would.
Would it improve your, would you have a better model conditioned by the assumption of equilibrium?
Yeah, the problem is you do not know the outer pressure which you have to know. So there are still parameters that have not been determined, and this modeling depends on the interstellar radiation field you assume, which is not easy to determine. You assume some normal nearby galactic value. And this interstellar radiation field might have a 3D component by nearby stars and so forth. So there are things still to be determined, but this is the way. There will go more in the talk by Mika very soon. I switch shortly to the last topic, and that is more massive stars. So if you go in that sequence, here you have the evolutionary time after the first hydrostatic core of the star is formed, and here you have the final mass of that star. Harald York has nicely put this together and saying that in the first phase you have an optically obscured phase, and then, for example, for a solar type star lying here, you have the Titori phase where the star is just contracting, and then main sequence and white dwarf and so forth. You see for the high mass stars, well, also you know very well, it reaches the main sequence well before it is no longer obscured. So we don't know what's going on there, at least not at the shorter wavelengths. So there's no evolution sequence so far. There are some proposals, and that's what we were trying to attempt. And for the people here doing accretion stuff, it's very interesting that accretion disks have been found in this part. So we are hunting for the accretion disk in this part. This is the great hunt currently, as you see in Nature, for example. And so we believe that if we could extend it here, we could believe that also accretion disks are the major ingredient in forming massive stars, but there are other proposals like stellar merger. If you look very short at very short times, you just see a filament, a thick millimeter flux block. That means there's a lot of dust here with a few hundred solar masses, and the only thing you can see, thank you, are jets coming out. That's the only indication of something is going on there. If you move them on, the star is starting to ionize its local surrounding. It's very compact in its configuration still, and this is the first candidate we found where you have something like a layer in front or a disk around it that might indicate that at this point already accretion disks may take place, and so you do radiative transfer modeling. And this is the image, this is an accretion disk around it, and this is the filament in front, and we believe from that modeling that it might be the first candidate for a disk around this very early phase. If you go to a normal massive star formation region, this is the galaxy galactic center, and then it's located here, it's M17. Many of you might know this. There are a few old stars sitting here. It's very messy because they blow away anything. And if you zoom into better resolution, it looks like this. And Rossini was investigating this lower part, and he found this structure, and I varied the contrast in the VLT image, and you see this structure, which is quite symmetric with a central star and something coming out. And this most discussed massive disk candidate, I would say, has a huge dimension. You see the low mass counterparts here, and we have modeled it, and the modeling even made it to the front page of AMA. Here you see the isodensity surface of the corresponding disk and the 2.2 micron image to compare with here, and we did a very long paper about this and came up that it is a circumstellar disk structure around it. We could identify that. The mass is unknown because the dust propagation. That's not the problem of the modeling. We don't know actually the dust that well, but for normal interstellar medium dust, it would be 10 solar masses or so. The object inside roughly might be the same. So the question is such a disk stable? And indeed, we did calculations calculating the tumor parameter, stability parameter in 3D, and it shows that these disks are not stable if they're thin. But if they're very thick, then you can reach the scalites and the lengths that we observe. There are line transfer modeling with the 3D line transfer code by Eric Tito from Harvard. Now, he visited us and produced first line maps. But I also want to draw your attention to another candidate for the later stages. Once the star has formed, it blows away anything. But if there was a massive disk, a remnant of that would be seen. And so we believe we have found the first candidate for this. It has also an inner cavity already, which points in the same direction. So we try to find a sequence covering this here. And to finish, there's a talk by Neil afterwards about massive star formation. The outlook is just roughly what can be done otherwise with radiative transfer, and that respect, light travel effects have been mentioned yesterday. If you have a T-Tauri disk, sometimes there's a wall going up and it's shading the disk, and this has light travel effects and then heating effects on in the outer part of the disk that can be observed. Also, we have next week we have a meeting where we treat dust-inspired galaxies. We actually want to model the full spiral structure of the dust sitting in that galaxy in a European project. I mentioned chemical networks. That will be very nice to see what is actually triggering the collapse, and also to find a clock, a chemical clock for the molecular cloud evolution. And there we also have a project with NASA to give you a feeling what else can be done with the modeling of the time-dependent 3D zodiacal dust distribution from the COBE mission data, and that helps for extragalactic and especially cosmology problems in reducing the error in those measurements. I finished with a few announcements of conference that might be interesting to you. In July, there's an ESO workshop on star and massive star cluster formation, and then a massive star formation conference in September with many people, 300 or so, if you're interested. Also interesting for some of you might be that at the same location 1 year later, there's a Cosmic Dust Near and Far conference, also very big. PAH's laboratory experiments, but also extragalactic work. And right after this, there will be a special workshop dedicated to radiative transfer coding. So those of you who are interested more in coding radiative transfer, just talk to me and we will have a meeting 3 days or so. And I just want to mention, and then I'm ready, that I'm also involved in a very big grid project where we want to develop a grid nationwide in Germany, but I know there are many other projects in other countries where we want to combine all computer software. You just submit your job, and the grid will know what to do with it. And that's all. Thank you.
Thank you very much for his quite impressive overview. I'm sure there are questions. Christian, would you speak up a bit louder, please?
I have 2 questions. They are from the data input in the FI. You say you infer the density structure from images. That means you have the information about the radiation field, then you do your radiation structure calculation, and then you have your density structure.
Right.
To me it sounds like not a very, there might maybe more than one solution for the problem.
That's not a naive question at all. I mean, we spent like, I would say, 3 or 4 pages in that paper where we did it for raw D to discuss especially this issue. But you're right. I mean, if you fit 140 parameters or so, you better make sure you have a unique solution. And we cannot exclude it, actually, because there are numerical errors that can amplify towards more than one solution. But our working hypothesis is also 90% of all the models that observers are using are 1D. If you have a working model, even if it's not a unique solution of the 3D density distribution, it's a good point to start and to improve.
Oh, I absolutely agree. Because, I mean, you have this problem.
Yeah, I should have mentioned that. There is an ambiguity problem that has to be taken care of. That's right. Yeah.
The second question is with your massive disk. I always thought it's quite a critical point to get the dust component in the disk properly. So, how are you treating that?
Yeah, we played around in that paper with the dust properties with an expert, Russian expert, Nima Semenov, for dust. And indeed, if it's carbon or so, the mass of the disk and many other properties we determine are different. So we made a model like saying, if we take this, we get this. But that's fair, I think. And my feeling was that this disk is quite hot. Different to other disks at low mass star formation where you get really cold regions. This is hot, so we have reason to believe that most of them are interstellar medium dust grains.
So what you are saying, you are playing with the chemistry of the dust and not the size distribution.
The size distribution as well is a topic. We assumed here one size. Numerically, there's no problem in including that. You see, normally the tradition is if you have a code, a 1D code, you wrote 5 years to really make it working and to apply it. And then you see there are structures that do not fit. So you have the choice of either fumbling around with the dust data to make sure it fits, or change the code to 2D. And many people in the history of the different communities stayed with their code and then have been very precise with the dust properties. That's one way to go. There's nothing wrong with that. But we, of course, have the 3D code. So the first thing we check is, what do we get if we assume a 3D structure, and then we vary the 3D structure rather than varying the dust properties. That can be done because we know numerically there's no problem in putting in other opacities or distribution of light.
So I just thought there has kind of has accumulated to a kind of common wisdom that
Yeah.
is, or that is like
What we usually do is we take the ascosilicate distribution, which is assuming a spread in the distribution, but then finally averaging over it and taking one particle this size representing that distribution, which is a bit long, but it's better than the mono-size distribution.
Two final questions. First Paul, then Arthur.
I just want to follow up this idea of the uniqueness of the inversion. In the study of X-ray clusters as X-ray sources, where it's the intergalactic medium, optically thin, thermal bremsstrahlung plus some mixture of collisional line excitation, a system which seems exceedingly simple by comparison in terms of radiative transfer, it's not possible to do the inversion without an assumption of something like spherically averaged and hydrostatic equilibrium. And so I just find it extraordinary that you can take this system which is optically thick and by assuming that it's a mixture of many different Gaussians, get anything. I don't understand how that works.
Yeah, I mean, it's a bit like Oka said, you have to find the key parameters that are sensitive. And I think that's the point. And the problem you described, probably it's not very easy to distinguish those solutions, and then you have no chance. It really depends on the problem. Here we have two independent information. We have see it in optically thick or maybe even thin absorption, but it's usually thick. And we see it in optically thin emission. These are two independent sources. The first thing determines the color density without question. We just go over it. So that's one independent solution. And you need another one. You can have approximations doing that, or we found out you can have the millimeter emission, which is sensitive not only to the temperature, but by this to the 3D extent. There could be any other mean that would help you. So that depends on the problem.
Okay, final question.
Yes, it's rather a comment or two. First about scattering. If scattering can be dealt with by iteration, then scattering is not important. If scattering is important, it needs to be dealt with something better than this iteration, because everybody knows that iteration on scattering converges extremely slowly. So have you tried any accelerated lambda iteration techniques?
Yeah.
Did it work for you?
The first thing we started was to really plug all the equations into each other and then have a large matrix. The second thing was that we had the lambda iteration on both the temperature and the frequency.
Accelerated lambda.
And then we accelerated it with a NIC method and other methods, and it accelerated, of course, but it was too slow. That was our impression. But at that time, we did it not with ray tracing, we did it on the finite differencing method.
The second comment is about the statement that I can never achieve doing the radiative transfer and the dynamics at the same time. I would dispute that. It's a holy grail. It's difficult, but I think it's doable.
You mean with the same resolution in all
Yes.
4+7 dimensions?
We can talk about that, but I don't think it should be given up.
Okay.
Well, with that hopeful note, let us thank our speaker again. And I call on the next speaker, who is Mika Jovala from Helsinki University, to talk about radiation transfer in molecular clouds.
So, what to say after Jürgen's talk about radiative transfer? Well, I have at least the line emission part is something that Jürgen didn't talk so much about. So I will be talking about radiative transfer and radiative transfer only, so no combination with HDE calculations or anything. I will be talking about the application of radiative transfer as a diagnostic tool, comparing some models with observations and looking both at line emission and dust emission, and also dust scattering as a separate topic. And at some points I will also talk about radiative transfer tools I've been using, or we have been using in Helsinki, and what development we are doing on those. So I think there's no need for any motivation for radiative transfer modeling of, so I will be talking about international clouds mainly. There's no need to do any special motivation because we know that there are several complications in these observations or interpretation of observations. There are optical depth effects, and there are variations in molecular abundances or dust properties or dust abundances, all kind of chemistry, depletion of molecules on dust phase and so on. And so there's a link between molecular and atomic species and the dust properties. One can of course try to model also those, but in the end one must somehow make predictions what observer would see in different cases. And finally there's the heating radiation that may come from outside or from internal sources, and then the source geometry itself is very complicated. So taking all these factors into account, we need some modeling of these interstellar clouds. And the idea is the basic familiar one. We take some crude physical model to radiative transfer, see what observers could see. We look at the infrared emission, for example, or dust or line emission, and then we do the comparison with observations. And this is an iterative process where we then refine the physical model, and hopefully then the end result is that we have a description of the cloud that also agrees with observations at the precision we have for the observations. So I will be concentrating on the radiative transfer part, but of course this is a very complicated field. Defining the, say, abundances, temperatures, velocity fields, and all things in the cloud, and then trying to define or find out those distributions based only on the observed properties, line emission and dust emission. So in fact the radiative transfer appears in this problem in several places, but I will be concentrating on the final part when we have some model and then we do radiative transfer to make predictions of these observables. Okay, so first something about dust emission. It was already covered by the previous talk, but I just remind you that there are these two parts, or actually three parts. There's a cloud model defining the density and the dust populations. It may be very complicated. You have different dust populations and size distributions and so on, and they may be spatially varying in the cloud. Then we have, okay, so the dust model also, which defines all these basic parameters, and also then for smaller grains we need specific heat because they are transiently heated particles and maybe even large molecules. And then we have a radius to field, which is difficult to observe directly, so we must do some assumptions what goes into the cloud, and then we do radiative transfer and get some spectrum out that can be compared with observations. Okay, so for the continuum transfer, I have been using only Monte Carlo, so we have done Monte Carlo on 1D, 2D, 3D grids first for large grains where we can assume that the grains are at equilibrium temperature, and then more lately then for smaller grains which are much harder problem because of the transient heating, which means that for each dust population, for each size interval we have for the dust grain distributions, we must also show the temperature distribution for these particular grains. And now I will mention 3 topics which were covered in a paper in 2005, trying to improve the basic Monte Carlo method using weighted sampling, then applying this accelerated Monte Carlo, which is basically the accelerated number iteration, and then using something that is called a reference field. So the weighted sampling means that we make some improvement in the way we create these photon packages. So you know that this is a simulation method. We create photon packages that are injected into the cloud, and then we follow how these packets move in the cloud, how they interact with the medium, and that is to show, say, the dust temperatures. So in weighted sampling, for example, taking a simple example, we have a spherical cloud, central radiation source, and then optically thick envelope surrounding this source. If this optical thickness is very large, then the immediate inner envelope that surrounds the source, radiation source, may be optically thick, and then if we don't sample the dust re-emission from this very small volume, then we basically decouple the source from the rest of the cloud, and we get quite wrong results. So one can have something like this. Here I've got number of photon packages using the simulation and the error, and if we do normal Monte Carlo, then the results are practically, there's no conversions, and the results are practically wrong because we don't have the, or we have separated the central source from the rest of the cloud because of this very poor sampling of the radiation field. Instead, if we do something simple, it would be like this figure, we simulate more emission events from the central region and less from the surrounding region. Then we can sample also this optically thick inner envelope, and then we get some convergence with much smaller number of photon packages, and then we also reach this normal convergence that is typical for Monte Carlo, 1 over the square root of n. So of course here the large difference between the unweighted and weighted case. We can go to even larger optical depth. That means that it's even more difficult to sample the free emission from the inner region. And in this case, we also made the additional constraint that the number of photon packages that are simulated from each concentric shell is equal. So there are small shells in the center part, but the number of photon packages emitted from those is the same as from the larger shells that are in the outer part. So, but within each shell, the position and direction of these photon packages is still random. But even with this constraint, we get this kind of convergence, which is now 1 over n, instead of this typical 1 over square root of n, which is what one would expect for Monte Carlo methods. And also, well, this figure should remind me just to say that this weighted sampling helps also in the case of very high optical depths, because with high optical depths there are 2 problems. There's this one problem is the sampling of the radiation field, or actually we want to sample the radiative coupling between different cells. And if we have optically thick cell, say this is one cell, and we emit photons from the center, they are all absorbed in the near the emission point, so there's no coupling between the neighboring cells. So all these photons are wasted. So one thing we did in this paper was to apply this weighted sampling also, so that we preferentially send photon packages out from the edges of the cells. So they have a larger probability of going over this boundary between cells and actually sampling the radiative coupling between different cells. So with that, we take a probability distribution for the initial position of the created photon packages. They are mostly on the edges, and that way, even if the optical depth goes to infinity, we still can sample this coupling between the cells. So that is one part of the problem with high optical depth, the sampling. The other part is this slow conversion, because here we have coupling between the dust emission and dust absorption, so that one cell is emitting photons, another cell is absorbing the emitted infrared photons, and this coupling also affects the dust temperature. So what we did is experiment with this accelerated lambda iteration methods in connection with the Monte Carlo. So in this particular case, the normal conversions, again, here number of iterations we have to do. So this is optically very thick, and in normal lambda iteration we must do many iterations in order to get conversions on the computed dust temperature. So in normal case we need something like 600 iterations. If we do diagonal lambda iteration, which means that we eliminate the absorption or emission absorption cycle within the cell from the equations, then we get something like this conversions. And if we further, so this was again a 1D model, so we have actually one shell and an inner shell and outer shell with which the shell is interacting. If we take these radiative couplings explicitly into account when we solve the temperatures of for these cells, then we get this tri-diagonal thing here. So convergence is already more than one. So we have 600 iterations here. Here we have 30 iterations, and also we do some experimentation with additional extrapolation. But in any case, it seems to be relatively efficient in this case. Of course, in 3D case, if we have a regular bit, then a cell has more than 2 neighbors, and then we must spend more space for storing all this coupling between the neighboring cells. But it's still doable also in 3D. And final thing was reference field. So this is an old idea. I think Bernes used that already for line transfer in 79, but I don't think that anybody has tried that for continuum calculations so far. So the idea is, when we do Monte Carlo, we don't calculate the total radiation field. We only use the simulation to calculate the difference between a reference solution and the correct solution. So if we have a reference solution that is close to the correct one, then the noise is correspondingly lower. So here the idea is also that we don't throw away the information we gather on previous iterations, because we have to do iterations, but we use previous iterations to build up this reference solution. So if one does normal Monte Carlo with a certain number of photon packages, after some time, then the sampling error dominates. So here we have convergence, and the sampling error means that we don't gain anything if we do more iterations. But if we include this reference field, then the sampling error goes also down with iterations, and we get higher accuracy. Okay, so I skip those. Also something about transient heated particles. So this is just to remind you that in all these cases there are two phases actually. One is the actual phasing of the radiation field, and the other part is we solve something. And in the case of dust, we are solving the dust temperature for dust temperature distributions. So that is and in some cases we need this iteration. But once we have solved the dust temperature distribution, then it's very easy to calculate the observables, so the spectra for any direction. I skipped this first example of modeling of infrared emission from some dark clouds, I go to the second example, which is a Linz 1780 cloud, where we have observations at different infrared wavelengths, and we want to model this now, also using 3D modeling. So this is interesting because here we have some contours from the IRAS survey, so 100 micrometer peaks somewhere here, and then the one goes to 60 micrometers, 25 micrometers, so one sees that there's a gradient across this cloud, and so there must be something. Either one has some the radiation field gradient along this direction, which causes that the shorter wavelengths are stronger at this side, or then one must have some change in the grain properties or grain size distributions. So here are just some observed 100 micrometers, 200 micrometers. These don't differ so much, but if one goes to shorter wavelengths, then the peak is somewhere here. And one can also note the temperature. This is a translucent cloud, so the temperature is not very extreme, but it still goes to something like 14 Kelvin. Okay, so this is now something that is still going on, and unfortunately I don't even have the figures for the modeling we have so far, but the idea is that we are fitting, first of all, the column density. We make an educated guess what the radiation field is, and then we model the column density. We must assume something about the density distribution along the line of sight, but then the actual column density is provided by the observation. For example, we can fit the 200 micrometers map exactly by changing the column density on each observed pixel. So there's a large number of free parameters, but they are largely independent from each other. So doing normal optimization after, say, 20 iterations, we have perfect fit. We can predict exactly the 200 micrometer map. If we do the same, taking into account also 100 micrometers, we already see that is no longer possible with any radiation field if we assume normal dust properties. So if we fit 100 micrometers, then in the central part we have an observed excess of 200 micrometers, and that is not unexpected. One would expect that there are some grain growth or something happening in the very cold core, and that should also cause increased emissivity in the submillimeter. So what we are doing at this moment is we are adding spatially varying dust properties. So we have a number of dust populations, and we vary the relative abundances of these dust properties, and we do that so long until we can fit all the 25, 60, 100, 200 micrometer maps. So the only problem at this moment is that there's the 200 micrometer excess requires really significant differences or changes in the dust properties. So further uses of continuum calculation, I can use them to make predictions for future observations of dust clouds at wavelengths where we don't really have much observations so far, for example, for the Planck and Herschel satellites. The problem here is that we really don't know enough about the dust properties at these sub-millimeter, millimeter wavelengths. So there are several effects that have been observed, but it's difficult to quantify them still at this moment. And then also one can use continuum calculations as input, for example, for chemistry, or as in this case for calculations of dust polarization. So this is something we did, and it was based on the Shaw and Lazarian paper. So what we added was we did these 3D simulations to calculate the local radiation field intensity, and use that together with the description given by the Shaw and Lazarian paper to predict the dust polarization, in this case for two Planck channels. One thing we didn't do here is we didn't calculate the actual local anisotropy of the radiation field, which is a crucial or central ingredient in this modeling, and that is something that we are doing at this moment. So Pelkonen is preparing another paper on the same subject. So then, especially on light scattering, so here I mean observations of radiation which is produced by dust scattering. So in goes some external radiation field, and part of that radiation is scattered towards the observer, and we observe the distribution of the scattered light. And there are 3 recent projects. One concerns near-infrared scattered light from quiescent clouds. Another on H-alpha line radiation, which is also seen towards dark clouds. And third is the carbon star, which is a bit outside our field, but we did some simulations there. So first on the near-infrared scattered light. So Foster and Goodman noticed in some observations towards dark cloud that, of course, there are some outflows and other things, but there is also this faint surface brightness, which they interpreted as a sign of scattered light. So we have dust cloud here, and in goes the normal interstellar radiation field, and we observe the scattered light, and here, combining, say, HK bands, we get also color variations because the optical depths are different for these wavelengths. So we did some modeling, Padon et al. Letter, and then we did another paper where we simulated these with 3D using MHD simulated data and doing the radiative transfer and looking at how this column density we estimate based on the scattered light, how it compares with the extinction we get from the, say, background stars using the normal method of looking at the reddening of the light from the background stars.
Very short question, that's an SPH simulation?
No.
That was real with magnetic fields and
Yes.
isolation.
Yeah. Actually, that is not so important. Important is that it's somehow not homogeneous. The actual result is not very dependent on the exact structure of the cloud. But the idea is that if one looks at the surface brightness as a function of visual extinction, then in the optical spin regime we have, of course, linear relation, and so it's easy to look at this observation of these 3 surface brightness values and estimate what is the column density. But also then when they start to saturate, we can extend the analysis to at least, say, 20 magnitudes of visual extinction. And then we did also some observations. These were done in last August. We looked at the filament in Corona Australis, made a map or image that in, say, H and K, and then applied the previous results, and then we looked at the, here we have the extinction from the background stars, here the extinction from the surface brightness, and we can confirm that what we see is actually the scattered light, and that gives a quite reliable estimate for the column density in this region. And the main thing here is that with looking at the surface brightness instead of background stars, we can get much higher resolution for these extinction maps. Okay, then about the H-alpha. So it was noticed recently that some dark clouds saw an excess in the H-alpha line. And here's an example. We have an extinction map in white contours, and then the colors show the H-alpha, and they are somehow connected with these clouds that are seen in the white contours, but they are also in some cases somewhat displaced with respect to the column density maximum. So we did modeling of this, and we can confirm that what is seen is actually normal dust scattering. So, for example, L7080 is a very good example. Here is the observed relation between visual extinction and then the intensity of the H-alpha line. And if we take the normal dust properties to normal radiative transfer simulation, taking into account the actual distribution of the H-alpha background, then we get more or less the same result. And this applies to optically thin clouds, and when we go to optically thick clouds, then of course the extinction of the cloud is the dominant factor, and then we get the relation which is decreasing instead of increasing. So that was published this year also. And then finally, Thomas Munttila is a new student in our group, and in his master's thesis he looked at this carbon star and looked at the scattered light from the extended envelope. So this is a nice object because at these wavelengths the central star is quite invisible, so for practical purposes this is just a dust cloud, and one can simulate the external radiation field that goes in and then look at the compare observations with the simulation. Actually the main work was done using just 1D models, but finally he just, in order to do some simulation of these partial arcs that are seen, then he did some simulation with the, say, 512 cubed models, but still the resolution is not really enough to resolve these thin shells. So that was just a bit of a side project. Then I have a few minutes time to talk about the light emission. So here the main difference, or there are of course differences, but concerning cloud model, of course, the important thing is that now we are also interested in the velocity field, because the line profiles involve also the radial velocity distribution on the line of sight. And then we need the molecular parameters, again assuming some radiation field and doing the radiative transfer. In these cases, we often assume also the temperature, because we don't really know what the temperature is, but of course we can also solve the temperature distributions consistently using the radiative transfer, because the molecular lines are the main cooling agent method there. Okay, so line transfer also we have been using Monte Carlo, and then also different accelerated number iteration ray tracing codes, and also we started in 2005 looking at the hierarchical models. So here I have just show again the simulation. So much of this work is also based on these similar MHD simulations. And so far, all what we have done is based on Unicrit runs. And we have looked at all kinds of statistics we can extract from these molecular line maps. Of course, they contain a lot of information, not only on the spatial distribution, but also then the velocity field. So during the past 10 years, we have had a few papers, and I noticed that Åke has been also involved in, I think, 7 papers we have published. Okay, so the 2005 we did some simple thing. We took a Unicrit MHD simulation, and we started to divide cells in order to find out how much we can reduce the discretization before that shows in the results. And the conclusion was that we can, just taking the local density field as the guideline for this discretization, we can drop the number of cells to 1/10, and so with 1/10 of the original computation time and 1/10 of the memory requirement, we can get results that are accurate to more or less 10%. So that is comparable still with observations. So that was the first thing we did on hierarchical grids. And then in 2005, I think we also started to looking at these AMR grids, which are different. So here we assume that each cell is divided independently. Here the idea is that we create the discretization as a hierarchy of regular grids. So we have still some subspace is filled by a regular grid where we have a constant cell size. That is a bit easier to handle. So we have for continuum transfer we have been using Monte Carlo, and then kind of characteristics for line transfer. And my first idea was that we want to divide this volume very rigidly so that each subgrid is handled independently. So we do a simulation within a subgrid, and then we save all the results, so the intensity on the boundary, and then we can forget about the subgrid, and then we can go, say, up one level in the hierarchy and using the intensity that is saved on the grid boundary, and we can go on with the simulation, and that would lead to very low memory requirements and would make it easy to parallelize the code. And also, one nice thing about the AMR is that then one can use different methods in different grids. For example, using the, say, accelerated methods, only the optical thick regions, or apply some weighted sampling in say, around sources or in very optically thick regions or something like that, or then doing simple sub-iterations for optically thick regions, because we have a subgrid which is optically thick, we know the intensity on its boundary, and we can make iterations within that subgrid, and that way the optical thickness of certain region doesn't necessarily mean that we have to redo the iteration using the whole model. And even going back to these accelerated methods, of course they are only used because we cannot save all the radiative couplings between all the cells. So if we have a very small subgrid, then we can do that. So we can do the sampling of the radiation field once, then we have the coupling between each cell within that subgrid, and then we don't have to do any iterations because we can solve the whole problem explicitly within that subgrid. Okay, so that is something that we started in 2005. We did also some comparison with Alex Rasumov, who was developing some code for cosmological purposes. But then after that there was a long time, and now we are only coming back to this problem of the AMR grid. So I think I spent a couple of months writing these programs for dust calculations and quantum line calculations, and also now Tuomas Luntula, who was looking at the scattering in this carbon star. I asked him to test my programs on that, but unfortunately he refused, and he did another program, and I think within a week he built an AMR grid where he can calculate nowadays light scattering. Of course that is a bit easier because you don't have to say anything about the result, you just take the outcoming photons and that is your result. Okay, so we did also some tests with line transfer. So I think we have more or less working programs also for line transfer on these AMR grids. And the idea is now, during the next year, start to look at these AMR, well, large-scale MHD simulations and sooner or later also AMR simulations, and taking this data and then applying these AMR and other radiative transfer methods to look at these cores that are forming these simulations, and then comparing those results with observations. Thank you.
Thank you very much. Discussion, please. Yes.
So how do you create the line profile for the line transfer? So I mean, is this called the redistribution of line?
Would you repeat the question, please?
Yes, the question was how I simulate the line profiles in the line transfer. So it's in Monte Carlo and also in these other codes. I have the line profile. I simulate line profile and actually all the transitions simultaneously. I have as a function of frequency then the intensity, and that is transferred to the grid. And always looking at the local velocity field, taking into account Doppler shift, the local absorption emission profile, and doing registry in Norway. So I saw for the whole profile.
You mean does it include the partial redistribution submarine?
Yes.
Any further questions? If not, let us thank the speaker again. It is now coffee time until 11:15, and yeah, that's right. And would I please ask Marek Abramovich to already set up his stuff in preparation? Okay, see you in half an hour.
Looks like enough people are working on stuff, but we don't have. Yeah. It's working out well.
Yeah. You don't know. then I can't provide. If this works, I have no special requirement. I'll give you 5 minutes more instruction anyway.
He has like the
Stop the bubble from breaking out.
really see that. When you open the public rate, they can
So that's really
yes, sure.
Oh, sure, let's do that.
Yeah. Your application was in my panel.
Yeah, I know.
I have to leave out.
Yes.
Unfortunately.
Obviously.
It's a big challenge. Yeah, I made the mistake of trying to read the proposal several times.
There was a pointer. I think there was another pointer. There was a number pointer, isn't it?
Oh, yeah.
An outlet.
Yeah. Exactly.
You see one?
Yeah.
How many are there?
One.
Only one?
There's only one.
What are those apples? Oh, I see. Oh. It works? Amazing. Then I'll need your help.
Presentation works. Equipment still works.
So when I get my truck, I'll ask you for help.
Check very presently that I'm not good in these things.
No?
I will give you help.
You're better than I am, that's, you just proved.
Can you check the previous list with mine? Because I gave needed after you.
Sure.
Took a couple of minutes, or even probably more. The break is after our room. What time is it? Quarter to 42. See if this signal somewhere. No, that's it. Very fine.
No, it does. After a few seconds, it does. So, okay, let me do it.
So they can have the
Problem with my computer is that the very old ones. They start.
Do you open it? Can you talk on this?
No.
Doing something.
It's doing something, and it will be doing something for a couple of minutes.
And that's Macintosh is much better because when you lock it, it does, I mean, it turns off the system.
Yes.
But the system is up. So the moment you open the cover, it works.
Yeah, but of course Windows accumulates all kinds of stuff, programs, which the system is checking before it's opened.
We can send each other messages.
Your is Macintosh.
What?
Your laptop is Macintosh.
Yes.
Would be there is no way from my laptop to send a message to any other one which is not the same operational system.
Oh, really?
My laptop is something like 12 years old.
But you already sent me email.
Yeah, but not through this
No,
connection.
but through email.
Yeah, sure.
Sure.
Yeah.
Well, we don't, all I'm saying is, we can talk by email
Yes.
without, even though we're next to each other.